So, good evening, everyone. Today I'm presenting my project on real-time EV dashboard integrating with an ADAS warning system. Our objective is to simulate how an EV behaves dynamically and how safety systems react instantly based on inputs and driving conditions. Now, explaining the system architecture, our system uses host target architecture where STM32 microcontroller processes all inputs in real time and sends processed data to the Python dashboard. Now, important is what we provide, whether throttle, brake, or sensor distance. It is not isolated. Parameter each directly affects vehicle dynamics and safety decisions. Now, this is the tech stack or hardware and simulation stack, which consists of STM Bluepill, PixSimLab simulator, which helps in both sensor and motor behavior modeling without physical components, and also analog sensors. And here we have used 4 potentiometers to model the accelerator pedal, and also the to model the accelerator pedal, braking pedal, and temperature and SOC. And along with that, we have used ultrasonic modules providing proximity data for ADAS distance sensing. After this, we have the EV controller module. So what happens here? EV controller converts driver inputs into motion using physics-based model. Important part is how these parameters affect system. Number one, throttle, acceleration input. So when throttle increases, motor torque increases. This directly increases acceleration and therefore vehicle speed rises faster. It would be demonstrated in the upcoming demo. And what comes next is brake input. When brake percentage increases, negative torque is applied. This reduces speed sharply. If braking is strong while throttle is low, the vehicle decelerates rapidly. And the next is driving mode, such as eco, normal, and sport. Eco modes limit torque output, so even high throttle results in slower acceleration. Sport mode increases torque gain, making the vehicle respond aggressively, even for small pedal input. Normal mode balances both. Now we come to the regenerative braking logic. So what happens here is that when brake input increases beyond a threshold, negative torque is applied. Higher brake, stronger deceleration. Moderate brake, smooth slowdown with partial energy recovery. Very low brake results in almost no regenerative effect and vehicle costs. Braking is not just stopping, it changes both speed and energy flow behavior. And after that, we have distance sensing, which consists of ultrasonic sensor. Ultrasonic sensor measures distance based on eco time. If obstacle distance decreases, system reacts faster. TTC reduces. Warning becomes urgent. And if distance increases, TTC increases and system stays in safe or advisory mode. ADAS safety logic says us that system calculate TTC, that means time to collision. If speed increases while distance remains constant, TTC decreases sharply. And if speed decreases, TTC increases. System becomes safer. And for the other hand, we have blind spot detection, which helps in keeping an eye on both left and right side. It also depends on threshold distance. Left-right distance should be less than 30 centimeter. It will give a warning trigger. If distance is greater than threshold, system remains silent. And up next, we have FSM. FSM changes behavior. Low throttle along with brake causes parked or idle state. High throttle causes transition to driving state. Sudden high brake or fault condition triggers faulty state. And for the last part, which we have is UART. UART works in following way. High throttle causes the dashboard speed to rise. instant, and high brakes. And if the brake is high, speed drops and energy flow changes. And if we reduce the distance, warning indicators turns on. Now we have the options of motor heating, such as if the motor goes beyond the threshold, it will show a warning alarm, uh, basically a red signal, which would indicate us that there is something wrong with this, and that's that. After that, now let's go to the UAT dashboard. Before that, we should talk about the industry relevance and what we have learned from this. So the primary thing is that cost-safe prototyping. Uh, this reduces this simulation methodology reduces hardware costs while enabling full logic validation. And we also got to learn automotive skills such as FSM design, ADAS algorithms, and real-time telemetry. And now let's get to the demo. So here it is, the demo part. These are the normal conditions. Now let us increase this. This is all a normal condition. Let us see what happens now. See, there is everything at normal. Brake is 15. As here, we have reduced brake and keep acceleration high. That means speed is also high. Now, what we can do? Let us introduce some faults or faulty states. Uh, at first, let us reduce the front distance and see what happens. So here I reduce the front distance and it shows a red indicator which is for collision and a white indicator which is for fault detection. Now let's see. Please wait for a few seconds. And here it is. You can see the alarm shows critical. So here is the collision alert, and it also shows a faulty state as we have caused a drastic decrease in distance. So that's a fault. And here it is. So this is the first case where collision happens due to reducing the front distance. Now let's try out some other methods. Now let us cause the temperature to decrease. Let us increase the temperature. We have already decreased it. Let us increase it. It will also give a fault state such as it is shown here, and here it is 105 degrees Celsius with a faulty state. Now let me show this things. Okay, so now I'm bringing the acceleration and the brake nearby each other. Let us see what changes it happens in the dashboard. Let us wait for a few seconds. Let us wait for a few seconds. And here it is. So the acceleration and brake is showing that they are both going towards near each other, and it also results in the negative torque which I was talking about in the presentation. So that's the case, and now let us get to the other demo. So after this, I'm keeping it back to where it was. Now let me Let me try with the left distance and the right distance. No, uh, so here, as you can see, there is a blue light glowing up. It would show an advisory here on the screen. Please wait for a few seconds. And here it is, the advisory. It is showing that the distance is nearby danger position, but still not in danger one. So we are getting an advisory alarm for this. Now, similar for the right distance. Let us do it. The yellow light glows up, signifying an advisory signal for the right obstacle also, or the car status. Wait for some minutes. It will show. And here it is. And here it is showing that what I have told, an advisory alarm. So this is more or less our project. Let me make it all go back to the normal positions. So this is more or less our project, which we have done using Pixim Lab and the other stuffs. Let me see if some changed. Okay, so please wait for some minutes. And as you can see, yes, here it is. So, okay, reducing, I have, okay, so more or less it's done. More or less it's done. And that's that. That's the project. And I'd like to thank my mentors and the whole team of Emertex for giving me this opportunity to complete this project. And that's it. Thank you.